Just want to say this is kind of a big deal because this is meetup number 50. All right. So since we got started last year, we've had a lot of meetups. This is number 50 in English. We've had other meetups in different languages, in Spanish, in Hindi, in Portuguese. Looking forward to do one in French and Russian in the near future, and any other languages we can get a hold of. Always a reminder to folks that are out there, if you have an idea, if you speak a different language, we are more than happy to have you on. So anyway, like I said, this is kind of special to be having our 50th meetup, joined by a very, very special guest, the head of engineering at Tecton, Ravi Trivedi. And Ravi, can you just tell us a little bit about yourself, what you're doing at Tecton? Somebody told me you might be hiring, looking for some new engineers. What's the deal?
Yeah, I think that was a bit of a title boost. I am not the head of engineering. We actually just have a VP of engineering who started
Correction. Sorry.
this week. But yeah, I am an engineering manager at Tecton. So yeah, I lead the product engineering team, which is one of the main teams here. And we are hiring in New York City and SF. And yeah, we've been growing steadily through COVID, and I'll go through some of the problems and challenges we're working on today. These ones are a little bit more like infra and platform centric, but yeah, I mean, if anyone finds this interesting, happy to chat more about what Tecton's up to, and I'll give you a little bit of an overview in the presentation as well.
Perfect. That being said, Ravi's got a lot of stuff we're going to be covering today. Put your questions in the chat. I'll be keeping track of those, and then we can continue the conversation in Slack afterwards if we don't have enough time at the end. But we want to, there's a lot of stuff that we got to cover today. So like I said, if you have questions, put them in the chat, and then we'll handle them after the webinar. So that being said, feel free to start sharing your screen. Let's jump into that presentation.
Sweet. Let me present. All right. I think you can. I guess you can probably see the Chrome window around it right now.
Yes.
All right. So I'm trying to get presenter view working with the full screen view. Let's see. So
shouldn't be a problem. While we're at it, just for folks that might be new, make sure you check us out on Twitter. You can check out our webpage. I'll leave some of those links in the chat while this is ongoing. As I said, for folks that are arriving, please leave your questions in the chat. We will get to them after the webinar. We'll continue the conversation with Ravi in our Slack. So if you're not in our Slack, jump in there because that's where we're going to be handling all the questions. Now we see you perfectly full screen, no Chrome.
Cool. Looks good?
Yep, looks great.
All right. So I'll be flying blind without my speaker notes. So let's roll with it. Unless there's a way to do that on slides, but oh well. All right, so you can see this.
Yeah.
All right, perfect. Cool. So let's begin. So yeah, data on Kubernetes 50. Bart, thank you for having me on this momentous occasion. That's a pretty big deal. That's a lot of talks, a lot of meetups. So excited to be here. So I'll start with a quick intro myself. So my name is Ravi. As I said, I'm an eng manager on Tecton's product engineering team. And we are hiring in New York and SF. I'll stop talking about hiring though, but
they're hiring.
Yeah, message has been received. I'm based in Tecton's New York office, but we are pretty much split between the two cities, and then we're slowly expanding in other areas as well. And before Tecton, I also worked at Google for a number of years. I was on Google Search, I was on Google Photos, right when it branched out and became its own product in 2014-ish, and then worked on some internal platforms as well. And then I also have the Feast logo down here. For anyone who's familiar with Feast, Tecton is like the primary sponsor and contributor to Feast, and the creator of Feast works with us at Tecton. So that's why I threw in the logo there. But let's jump in. So what we're going to go over today in the next, hopefully within a small enough window of time that Bart doesn't kick me off, we're going to go through, a quick feature store 101, which will set the foundation for what we're going to talk about through the rest of the presentation. And then the challenge that we're trying to, what's the problem we're trying to solve, and really the journey to Kafka. And then finally, we'll, once that journey completed, we had a number of surprises at the destination, which is a pretty big topic on its own. And then at the end, we're going to have some takeaways and conclusions. So Feature Store 101. So these are quotes I took directly off the Tecton website. But Tecton, we are building the enterprise feature store for machine learning. And so what we want people to be able to do is build a great library of features, serve them in production, and do it at scale. And what we mean by this is we want to enable operational machine learning. So it's not enough to train a model and use it locally, but we want to be able to, we want companies and products to be able to introduce predictions and models at every corner of their product. And we want to be able to do it at scale. And so I'll go into a little bit more about what that means. Again, this is from our website, but the basics of a feature store are this red box here. So a feature store ingests external data.
Ravi, really quickly, I don't know if you did you try to switch to the second slide? Because we're still seeing the first one.
Okay. You're still seeing the...
Yeah, going full circle with Kafka. Yeah.
Oh, really?
Yeah.
That's not right. Hold on.
It's all good.
Oh man, you missed all my beginning slides. So you can see this now, right?
Yeah, we can see it now. Yeah.
Okay. So maybe I don't know what was going on there. So if we're okay with... Yeah,
it's all good. We see the Chrome thing. It's no big deal. Yeah.
All right. So we're good? How's this look?
Yep.
Okay, cool. So yeah, so these were the slides I was showing before. So when I was talking about logos and stuff, this is what I was talking about. Let's see. You can see the agenda slide right now?
Yep.
Okay, cool.
Yep. Great.
So yeah, this is the slide that I was referring to. Oh yeah, this is the one here. So Feature Store 101. So a feature store is essentially what's in this red box here. And so, this is an overly simplified diagram, but the high level fundamentals of it are that feature stores ingest data from external data sources. And so typically this is batch and streaming data. And the feature store then manages the transformations from that raw data to curated features. And so the feature store manages the transformations, the storage of that data, a bunch of monitoring and platform type of functionality, and it basically maintains an entire feature registry for you. And finally, the important part is feature serving. So we're going to focus a lot on this quite a bit. So there are two fundamental modes of consuming features from a feature store. One is primarily for model serving, and one is for model training. And I'll focus on model training first. So this is a very iterative workflow. So people fetch features, and usually it's like large sets of data to train a model with. And so they are iterating, training models. They'll fetch a big data set, save some for testing, and use some for training, and then they'll iterate. And typically these are data scientists doing this. And where a feature store comes in is, once you have that perfect model, you want to serve it in production. And so ultimately you want it to be able to make predictions in real time to back whatever product experience you're building. And that's where model serving comes in. And so this mode of feature serving involves targeted feature vector fetches in, single-digit milliseconds or double-digit milliseconds to fetch features for an incoming request, let's say, to your website or something, and run them through your model and make a prediction. So I'm going to drill even, more simple here. The stream and batch sources are an input to your feature store. You have your transformation layer, and then you want to write to an offline and online store. And once again, offline is typically for model training, online is for model serving. And so the requirements of the offline and online store are quite different. Now, I'm talking about these all in the abstract, so I'll go into it a little bit with some concrete examples here. So for streaming sources, you might have, Kinesis, Kafka, which I'm sure many people here are familiar with. And then for batch sources, it could be data on S3, data warehouses like Snowflake, for example, Hive. And on the feature store side, your offline store could also be a data warehouse. It could be S3 again. And in the online store, you typically want something like a low latency key value store because you're doing fairly targeted lookups. So DynamoDB, Redis, these are all examples. And today we're actually going to focus a bit on DynamoDB later in the presentation. So just keep that in mind. So let's break down the problem. We are just going to focus on batch data sources to offline store. And we have a transformation, or we need to support a transformation layer between the batch data source and the offline store. And so, we need some sort of compute engine to do this. And there are a lot of options that, to accomplish this with. And I'm just going to focus on one today, but by no means is this the only option for doing so. And so today I'm going to focus on using Apache Spark. And Spark is fantastic for data lakes. For those of you who aren't familiar with it, it's distributed data processing engine. It's like a pretty much excellent MapReduce on steroids, and it has a variety of support for both connectors and data sources and sinks, and it's become quite industry standard in recent years. And so I'm just going to focus on Spark today. So Spark has an excellent API. You can write standard SQL queries, and there's also an API called PySpark, and that lets you write queries like this. So, for example, you might read some Parquet data off of from S3, and so let's go with a hypothetical store that's called Acme Shop, and you're going to read some orders, some historical order data from it. And let's say you want to make a set of features that are you're counting fraudulent orders per day per store. So maybe this Acme Shop has multiple locations, for example. And so you can write a query that's, in this case, you use the group by function. You're going to group by a store ID and date, and then you're going to aggregate a sum of the is fraud column, which is just zeros and ones. And then ultimately, you're going to write it to another S3 bucket. Let's call it offline store.io, and you're going to partition it by date. So, this is the world's simplest feature transformation. So what you could do with this then is generate a training data frame that, likely there are many more features that are involved, but you can generate a training data frame and train a model that is based on some historical data that you've fetched. So, is the problem solved? Definitely not. I left out a very important detail in this example, which is the online store. And we need a way to write from the batch source to the online store, because remember, for the offline store, typically it's not super latency sensitive. Data scientists are fetching large amounts of data to train and test their models with. The online store is targeted feature lookups. And so the requirements there are low latency targeted reads, low staleness. And by that, I mean the data in the online store, we want it to be as fresh as possible and as up to date against new data that's come into the batch source. And so this is, of course, configurable. So you could have a pipeline that runs once every hour, for example, and updates the online store, or you can even do it more frequently or less frequently than that. And the other one is parity with the offline store. And this one is critical. So we need the online and offline store to have the same data. So if there's no parity, then you risk having a completely different set of data that you're training models on than compared to what you are actually using for inference. And this can lead to a lot of poor model performance. And this is one of the fundamental pillars of a feature store. So you have a few options. You could either write separately to the online and offline store, the red arrows here. You could also write to the online store first and then copy it to the offline store. And then you could do the reverse as well, offline first and then copy to the online store. And each of these have different trade-offs and pitfalls. So, really quickly, the writing separately to online and offline approach, the big risk here is online-offline consistency. So you have to be careful because depending on your approach, you might end up with drastically different data in the online and offline store, and that could be very problematic. The other option is write to online first and then copy to offline. But the thing with an online store is they're typically, more expensive to run. They're not really meant for doing scans or large queries like batch queries. So you're probably using it wrong if you're scanning large numbers of rows to ultimately write them to an offline store. And then if you go with the offline store first approach, you're violating the freshness requirement. So you want the online store to be as up to date as possible because that's the one you're using for inference. The offline store, it's a little less sensitive because typically it's being used for training. So that really is a non-starter for writing to the offline store first and then copying to the online store. So based on these, we go with the first option, writing to the online and offline store separately. And I'll talk a little bit more. It'll come together why, what we did to mitigate online-offline consistency or inconsistency. And there's one critical piece that I'm leaving out: streaming data sources. So where do they fit into this picture? Streaming data sources are a little bit different. So if you are using a streaming data source, it probably means you have a pretty consistent flow of data and you probably care about freshness quite a bit. And so you want the streaming data source to be updating the online store directly. And in order to do that, it introduces a pretty different data flow through this pipeline here. And then typically streaming sources are paired with a batch source that's used for historical data. So this could be, because stream sources typically have some retention window. So for historical data, you'll need it paired with a batch source. So typically that's something like a log from the stream that is just writing to a batch source. And you also want it for backfills. So, the first time you define your features, you might want to say backfill the last year of data, for example. And so for that, you use the standard, batch to offline flow. And then again, there are batch only use cases, which are what the red arrows are here. So I talked about Spark before, and there's a lot of actually background that we can go into, but I do want to be sensitive to our time constraints here. So one thing that Spark provides is Spark structured streaming. So Spark actually does have a stream processing engine out of the box. And so the nice thing about using Spark for both streaming and batch use cases is that you can actually share the transformations. So, that super simple PySpark transformation that I showed in the one of the earlier slides, you can use that for both streaming and batch transformations. There are some limitations to what you can't do in streaming transformations, but generally speaking, you can use the same set of transformations. And this provides a really nice property because it gives you some guarantees for online-offline consistency, because you're not writing the same query or the same, you're not processing the data in two separate ways. You're using the same query or same transformation to process the data that's going to the online and offline stores. So with that, I'm going to dig into what I mentioned before, is writing to DynamoDB. And so there's an important thing to know with Spark, and that is that it has many different sources and sinks supported out of the box. So, writing to and from S3, for example, is pretty much trivial and natively supported by Spark. But writing to something like DynamoDB, there is no out-of-the-box support for it in Spark. There are plenty of examples. If you Google Spark DynamoDB, there are plenty of examples of how to write to it. But you do have to build some of the support yourself. And there are open source offerings as well, but that's actually this is the problem that I'm going to dig into here. And so there's one critical set of functionality here in Spark that we relied on for this approach here, which is this for each method. And so in Spark, you can just provide a UDF that is invoked on every row when you're processing a data frame. And this can be used for both batch and streaming. And you could pretty much put whatever you want inside the UDF. So you end up with something like this. Also, Bart, yeah, give me a time check if I'm going too fast, too slow. Feel free to jump in. So you end up with something like this. And this is actually just an example that's almost verbatim taken off the Databricks website. You have a write to DynamoDB function here, and then this get DynamoDB function gives you a Databricks client, and then you just have a put item operation here. So this actually works out quite elegantly. So you just invoke this write to DynamoDB function on every row that you're writing, and then you write to a table. And so this actually works quite well. You do have some credential management that's needed to plumb through your access and secret keys without having them out in the open. But it seemed like a pretty elegant solution. And so now the pipeline we have, it looks like this. So on the top, we have stream sources writing to online stores. And so in Spark and PySpark, you can use dataframe.writeStream.forEach, and then invoke the UDF on every single row. And it looks exactly like the example on the previous slide. Then for batch to online store, it's a slightly different API, but you still use forEach, and you would just invoke dataframe.forEach and invoke that UDF. And then for the batch to offline store, you would use something more similar to that, the initial query that I showed where we were reading and writing both from S3. So there's no need to use the forEach function. So at this point, we're feeling pretty good about this approach. We're saying like, this is very elegant. We're just going to use this, custom writer, and it's going to be invoked in all the different use cases. And, we'll have complete guarantees over online, offline parity. And, we're living the dream. This is perfect. So at this point we say, okay, the prototype, we think it works. And so we start developing. And by developing, I mean, there's a design process, and we start researching all the ins and outs of what we need to do. But we begin our development. So, we start with a clean slate, and we start with and I got rid of the get DynamoDB function here, but we start with a clean slate function that's just this write to DynamoDB method here. So what do we actually need to do to put this into production? Because this is fairly simplistic. This also is a hard-coded example here, but keep in mind, a feature store is not, like if you're building a feature store software as a service product, you are using user-defined transformations. So these, the query and the schema and everything here is all based on user-defined definitions. And so there's a lot of parameterization, a lot of metadata that we need to plumb through, and a million other things. So when we start actually looking into the requirements, it started painting a very different picture. So, for one, you have to support several different feature types, and like Tecton and any feature store support multiple different types of features that all have slightly different requirements for writing to the online store. You also have to deal with type conversions. So DynamoDB has a pretty specific set of types, and so does Spark. So you need to include this logic in the writer. Finally, or not finally, but third, you need to pass in a bunch of schema metadata. So like I said, this is all user-defined definitions that you are implementing a generic writer for. So there's a lot of metadata that needs to be passed through in order to tell this writer what to do. Maybe you need to support writes to multiple tables as well. And you're probably developing a lot of library code at this point. So you need to, factor some of it out into shared helper libraries, which, as far as dependency management goes and, reliably serializing code, like the way that Spark invokes all of these UDFs is that it serializes it and sends them to the executors that are actually doing the computation. And we did run into a lot of issues with, unexpected serialization of dependencies or missing dependencies. And so that was another big issue. Then you have, compound partition keys. So you're not just using standard types, you might be using something more complex. DynamoDB, for anyone who's worked with it, it does auto scale, but the auto scaling is not instant. It does have a eventual ramp up. So you might need to handle some retry behavior. The client that was used in the previous example, it does have built-in retries, but sometimes you also need to do manual retries. Then there's an entire logging and monitoring story. Like, what is your observability story at all? How do we reliably run this in production and have a good visibility into what's going on? How do we investigate issues? And how do we have control knobs? Like when there's something that goes awry, how do we stop it? Writing to an online store can be expensive for large amounts of data. So we need to have very powerful controls in place to reliably run this system. And then how do you debug it? Can you even get recently processed records easily? And all of these problems started painting a very different picture for this approach. And what started as a simple function that was this nice little UDF evolved into a kind of behemoth of Python code that we were running, and it became a bit unwieldy. And so as you can imagine, supporting all these things in a single function, or you can wrap it up nicely in a class, but it was not elegant after a while. And so we ended up with this kind of, this was the different phases of this approach. And I like this graph, and it's somewhat generic actually to a lot of projects, but pretty much we started with an approach and our confidence grew very quickly. And we had a prototype that it works. And pretty much at that point, our confidence was at a peak. And we said, this is great. Then as we started designing and developing it, our confidence started going down. We were saying, oh, I don't know, these additional requirements are quite a lot to take into consideration. And then we had an initial rollout. And so, initial rollout, if it doesn't go smoothly, you enter this pit of despair where you're like, this was a mistake. I regret my decisions. We probably wasted all this time. This is a big problem. But, you push forward, fix some bugs, you do a second rollout, and then your confidence increases again. And you're saying, okay, I think this system could work. Let's stick to our guns. And then you have your first outage. Confidence drops again. And you fix some more bugs and confidence increases, and then you probably have a second outage. And then again, there's a drop in confidence, fix some bugs, and then maybe you have a third and a fourth. But eventually you reach a point of no return where you've kind of lost confidence in the solution, and you enter this final phase, which is, this needs to go. It's not good. And so this kind of concludes our road to Kafka part of the presentation. So the search begins for a new solution. And I haven't said anything about Kubernetes yet. We haven't really talked about Kafka at all yet. And that's the promise of the talk, but I promise you I'm getting there. So what are the requirements here? So we wanted to keep as much logic outside of Spark as possible, because that's what got us into this problem in the first place. We have to have streaming support. We have to have excellent reliability and observability. We need to be able to reprocess records and easily go over historical data. We need to have it completely scalable to pretty much any volume that the user of the feature store might throw at us. And then we want to just do more with less. Like, we don't want to reinvent the wheel if we can avoid it. So we want to use as much off-the-shelf or industry standard technology as possible. And that naturally led us to Kafka. And we did have some alternatives, but I'm going to focus on Kafka. That's the name of the talk here. So, this is just a screenshot from Kafka's website. It's clearly an industry standard offering and technology, and it's an excellent streaming platform. A number of the streaming sources that customers use are Kafka based, and it's battle tested. So, it checked all of our boxes for this project. And so we look at the requirements, and the nice thing is that Spark has first-class support for Kafka syncs. Streaming is pretty much like Kafka itself is a stream, so or a streaming platform. So stream to stream writes, not an issue. Observability and reprocessing, it's pretty much trivial. You can just tail any topic. You can, set whichever offset you want to go back to, and then just read the data verbatim from it. There's a lot of off-the-shelf monitoring that's offered as well for Kafka, so you don't really have to think about that too much. It's scalable on many dimensions that I'll go into in the subsequent slides. And it's battle tested. There's no surprises. It's industry standard. So we ended up, I actually removed the offline store because that's not the interesting part here, but we had a write path originally that was from stream to online source and then batch to online store. So we had this for each method. We weren't happy with it ultimately. And so what we ended up with for Kafka was something like this. You would still be able to use the same queries in Spark. So the same trend, like the online offline parity guarantees that we got with using the same Spark API for both streaming and batch sources, we still had that ability. And you could just write to Kafka, and the Kafka sync is included out of the box with Spark. So this was, there's no custom logic in Spark, and it met that requirement. And so we could keep all the complicated logic outside. And this is where the Kubernetes aspect of the presentation will come in. So, you send this data to Kafka, run a Kafka cluster, and then in Kubernetes, we run a Kafka consumer. And then the consumer is the thing that writes to the online store. And so this has a lot of nice properties because now all the complicated logic is running in Kubernetes. It's not running in ephemeral Spark jobs. The observability story is a lot more promising. You're also not constrained to any of the languages that are support with Spark. So you can use anything that can read from Kafka, and Kafka has a number of client libraries. And for those of you who are not familiar with Kafka, I'll also provide a quick Kafka 101. So starting on the top left, Kafka has producers and consumers. So you can have any number of producers writing to Kafka, and you can have any number of consumers writing to Kafka. And the organizational unit of Kafka is a topic. And a topic is just a log. So when producers write to a topic, the end offset of the topic is increased, and there's a record appended to the end. And then when a consumer consumes from the topic, Kafka keeps track of where it has consumed up to, and then it'll read some records off of it, and then you'll commit to a new updated offset that you've read from. And then, excuse me, going up to the top right here, this is an important part. Topics are partitioned, and also a consumer is not just like a single consumer thread. Typically, you have a consumer group. And so when you write to a topic, that topic can have any number of partitions, like it's configurable. And based on the key of the record, it'll get assigned to some partition. And then you also have a pool of consumers, and Kafka automatically balances these consumers between the different partitions, and it assigns them to a given partition. And from time to time, it also rebalances. So this actually has a really nice horizontal scalability property. And pay attention to this partitions and consumer groups part, because it'll become very relevant in the upcoming part of the presentation. So this was a big jump from the previous slide, so we'll spend a second on it. Our new setup looks a little bit like this. So on the left side, we have the producers to Kafka. And these are Spark jobs. So each Spark job could be serving a different purpose. Some could be streaming, some could be batch, some could be like historical backfills. They're all running independently, and they're all writing to a Kafka cluster, to some Kafka topic. And so on the left side, we have the Kafka producers. Then on the right, on the right side, running in Kubernetes, we have implemented our own consumer and the consumer's sole job is just to pull records off of the Kafka topic and write them to DynamoDB. So on the right side, we have the Kafka consumers. And the nice thing about this is, again, the Kafka consumers are running in Kubernetes. They're stable jobs. They're easy to easy to debug, easy to run in production, easy to get monitoring for. It's a very easy to run setup, or is it? Oops. So you have some decisions to make at this point. What is your organization of topics? Do you just have one topic per Spark job? Do you have a single mega topic that just everything writes to with a large number of partitions? Maybe there's some other option. You also need to figure out how many consumers do you have. So, each process that you're running or each pod could have some number of Kafka consumer threads, and you need to figure out, what's the number of threads and consumers that you can support. And then you probably need multiple replicas in your deployment, so you need to figure out that as well. And typically this will be proportional to whatever load or whatever the volume of data that you're processing is. So I'm going to focus on the right side here. And let's suppose we go with the mega topic, because the reason we didn't want to go with a topic per job is because topics they're not expensive, but they do occupy resources in the Kafka cluster. And some jobs are, the job could last 2 minutes or the job could last 5 hours. And so you might end up with some topics that are extremely underutilized. So we go with the mega topic. And I've given 8 partitions here, but the number of partitions in the topic is configurable. So I'm using 8 here to illustrate. And then on the Kafka consumer side, within a group, let's say we have 3 replicas in this deployment, and each replica runs 3 consumer threads, suppose. Now, this is all empirical. We're still figuring out, what's the throughput, we need to do some load testing here. And so this is just our starting setup. Now, I'm going to zoom in on the left side of the previous slide now, which is the Kafka producer side. And actually, sorry, let me go through one more detail here. The consumer group is an important part here. So when you create a consumer, you specify a group. It's just like an ID. And if you have any arbitrary number of consumers running in a single group, Kafka treats them as a pool of consumers and it bounces among them. If you were to introduce another set of consumers that have a new group, then they read from Kafka completely independently from the first group. So Kafka internally manages how far along in each topic and each partition a given group is. And so this is what allows multiple consumers to run independently, reading from the same data source. And Kafka internally will just maintain the offsets and how far they've reached independently. So I'm going to go back to the producer side now. So remember, I was saying that we're using Spark for streaming. We're also using it for batch, and then we might even be using it for backfills. And so what do I mean by this? So streaming jobs are pretty much always running. And so they're constantly running. Some of them might be fairly high throughput. Some of them also might be fairly low throughput. And then batch jobs might be a scheduled job. So maybe there's something that's just running once an hour, once a day, once every 12 hours it could be. So it's a fairly predictable periodic workload. And then backfills are another one. So, if you're bootstrapping a set of features, then you might want to, let's say, compute features from raw data for the last, let's say, 3 years. And this could be, quite a lot of data. And so you have these three fairly diverse workloads that are going through the cluster. And you'll notice that each producer to Kafka is assigned to some partition. And it's assigned to some partition based on the key of the records being written to Kafka. So each record has a key and a value. And I'm going to zoom in on the case here where two different jobs are writing to the same partition. And so here we have a streaming job and a backfill job writing to the same partition. And this is what gave us problem number one. Each partition is a FIFO queue. This is both a problem, but there's also a feature and a core functionality of Kafka. But I'll dig into this more. So what are the requirements around streaming jobs? We want them to be processed as soon as possible. And remember, if you're using streaming and you want to write to the online store, freshness is the name of the game. So you want to process these records as soon as possible. It's a very different set of requirements than a backfill job, which is potentially high volume. And the turnaround time is not as important because you just want the data to be processed eventually and there's no strict requirement there. So let's zoom in on this problem. A given partition is just a set of offsets. And so on the left here is we have older data. So you might end up in a situation where the backfill job has completely flooded the partition. And then you have this, so the backfill job are the red squares here. And then you have this single stream event that's trapped amongst all these red events. And so the streaming event has no way to jump the queue. And it has no choice but to wait for the backfill jobs to be processed. And so this introduces a pretty interesting problem where you might have completely separate workloads. And maybe you start running a big backfill for some set of features. And all of a sudden you'll start noticing some stream-based features are not being processed at the same rate, and the data is getting stale, or the features are getting stale. And you're starting to wonder, like, how does this happen? And it's because the stream events might be caught in line behind a bunch of backfill events, and there's no way to jump the queue. So this is pretty much, painted a big problem for us. And what we ended up doing instead of a mega topic is we went to a workload-based topic. And so we would have a separate topic for batch, a separate topic for streaming, and a separate topic for backfills. And so this works reasonably well. We're like, cool, well, all the streaming jobs will write to a single streaming topic. And for that topic, we want throughput to be extremely high. And then similar for batch, they'll all write to a single batch topic, and they'll have their own consumer group. And then backfill will all go together in a backfill topic. And we can provision these independently. And so we have some isolation between the workloads using this setup. So this worked reasonably well, but then the actual provisioning problem became an interesting problem on its own. So this leads into our next challenge, which is spiky workloads. So let's look at the backfill scenario. So you have a partition, and for periodic, this could apply to stream jobs. It could apply to batch jobs as well. But it's most interesting in the backfill scenario. So maybe let's say 1% of the time, the topic and the partitions are completely flooded, like they're just hammering through data. The other 99% of the time, it's completely idle. Like there's no usage whatsoever. And so, what do you want your utilization to be? And also you have to provision for this on the consumer side as well. And so you could either be over provisioned and just permanently have, way too many resources, and 1% of the time they're actually used. You could manually provision it, or you could use auto scaling. So there is like CPU-based auto scaling in Kubernetes. But for that, you need to maintain enough headroom in your cluster as well. And so what we end up with is, differently scaled consumer groups. And so, the streaming group might have the highest set of resources assigned to it, because we need those events to be like written to Dynamo as soon as possible and read off Kafka as quickly as possible with no delays. Backfills might be under provisioned because it's a smaller pipe that we have to get data through, but the requirements are not as latency sensitive, or the turnaround time is not as critical. And then we could also provision batch independently. And so, this is like an example of manually provisioning it. But like I said, you could also use CPU-based autoscaling in Kubernetes. But there's an important consideration that I haven't really touched on yet, which is that if you're running a SaaS product, you're probably running multiple versions of this. So, if you want to maintain a lot of headroom to allow autoscaling in your Kubernetes cluster, any kind of aggressive bin packing you do will be savings that are passed on to your customer. So, you could maintain a lot of headroom, but you want to keep things, as resource, using the least resources possible, because those are savings for you and savings for your customer. And so I'm going to, again, focus on this backfill scenario here. So let's say, you have a fairly small set of provision resources for your backfill topic. And so, what if you have a couple backfill jobs that are mapping to the same partition? So, this is working as intended, because we don't need to turn these around in too quick of a time, and we just need them to be eventually processed. But what if one of them introduces a problematic record? And keep in mind, with the feature store, you are using user-defined transformations on user-provided data. So you can't predict everything that can go through that will be written to your Kafka cluster. And so, you can have reasonable confidence and lots of testing and lots of, condition handling. But at the end of the day, there are going to be corner cases that come up that you haven't seen before. And so this introduces a pretty interesting problem, which is what we call poison pills. And you have a few options for this. So one option is you just skip the record. If there's an issue, you just skip it and move on. Another option is you just attempt to reprocess it and hope that it fixes itself when you process it again. And then the third option is, you fire an alert or something and require manual intervention. So, none of these are actually very good options. If you skip the record and move on, remember, we have a requirement for online and offline parity. So, depending on the prevalence of these poison pills, you might end up with a significantly different distribution of data in your online store that's processed by Kafka compared to your offline store. And so you probably don't want to just blindly skip it and move on. The other option is you just reprocess the record. And this is, you're kind of just hoping that it fixes itself. And when I was at Google on SRE, there was a saying that we like to say, which was, hope is not a strategy. And this is pretty much hope as a strategy, and you hope that it fixes itself. So this is not a very viable solution. The final option is you alert and require manual intervention. And obviously this is labor intensive. It's very high, very toil heavy. We clearly don't want to be doing this. So, as you can see, none of these are really good options. And then I think what makes this problem a lot worse is these could be surfaced at a time when the actual job that originally wrote to Kafka has completed. And so remember, there's two stages here. There's a Spark job that writes to Kafka, and then subsequently Kafka has to process all the records that were written to it. And this brings us our fourth problem, which is an asynchronous separation of concerns. And what do I mean by this? So you kind of have two worlds here. You have the job writing to Kafka, and then you have everything consuming from Kafka. And depending on the setup, the user might say, cool, the job is completed. All my data is ready to go. But depending on your provisioning and all of the knobs we described in the previous slides, the actual Kafka consumer side of the picture might take a while to process your data. So in reality, you might actually be only partially completed, but as far as the user sees, they're like, okay, cool, my job's done. This brings on a very key distinction, which is the job does not mean all the records have been processed. We might even throw in a poison pill into the mix and say like, okay, the jobs haven't been the records haven't been processed, and also they're just going to start failing at some point. And there's, from the user's perspective, everything looks good. And this is a pretty big problem. It's a pretty poor user experience, and it's a little difficult to reason about in an elegant way. And so one option is we introduce these hint messages. So at the end of the job, you might just publish like a single predefined format message to the Kafka topic. And that message tells you, okay, if you're reading this, it means we have finished this job. And then you can use that to update some metadata that will inform the user of that their job is complete. So we sort of can work through that problem using these hint messages. And then we have the fifth and final problem we're going to go over, and that is that Kafka is more expensive than not using Kafka. So remember, if you're using Spark, the jobs cost roughly the same, regardless if you are writing to a Kafka sync or a custom sync or custom UDF. Assuming the processing record latency per record and the general resources, the requirements around them are similar, you can assume that the Spark jobs don't have a very different cost. But you're also running a Kafka cluster, and you're running a pool of Kafka consumers on Kubernetes, like for all the different workloads, and some of them have low utilization. And so suddenly you have all these flat or fixed costs in addition to the cost of the Spark jobs. And then the other thing is like a Kafka cluster is it's not super cheap to run. Even if it's idle and it has fairly small nodes, it still needs to be constantly available and constantly running. And so it has a non-trivial cost of operation. And so this brings us back to our original question that we set out to solve. And are we really doing all this to avoid using a UDF? And if you remember, one of the requirements was we want to do more with less. But with all these additional functionalities that we've built, we're kind of doing more with more. And so it really makes you question if this was the right approach for this given problem. And so I bring back this graph again, where we started with an idea, we investigated the approach, sounded great. We're like, cool, Kafka is an elegant solution, it's industry standard, this is great. Then we arrived at a prototype that works, and we were like, cool, our confidence is at an all-time high, this is going to be great. We start developing it, confidence goes down a little bit as you start throwing some corner cases in, and you do an initial rollout, and you're affected by one or more of the problems that I've described, and you enter this pit where you're thinking, this was a mistake. Why did I do this? And then you do a second rollout, fix some bugs, you persist, you prevail, and then fix some bugs, increase your confidence in the solution. You have a first outage, second outage, and then at some point you reach the conclusion where you're thinking, this probably isn't the right solution for what we're doing here. And so with that, I'll go to my takeaways and conclusions, and we're pretty pressed on time here. My takeaway is that Kafka actually was quite fantastic. It just wasn't the right solution for this use case. So Kafka itself actually scaled very well. Like the operation of the cluster, its ability to handle the different workloads, its reliability, its availability, it actually wasn't much of an issue. Like it was actually quite fantastic. But there were a number of considerations in the usage of Kafka that played a role in this. So one is, what was our expected utilization of Kafka? if you have fairly low utilization, then you need to consider the costs. So this is the fourth bullet here. What's the ROI on the baseline cost of running Kafka plus this consumers over an alternative solution if you have fairly low utilization? And then the other thing is, what's the expected diversity and predictability of workloads? Like, and how are you going to handle that? What are the data integrity requirements? So this goes back to the question of, what do we do if we had a poison pill? Do we just skip it? And if you are processing a workload that can just skip over bad data, then cool. That might not be an issue for you. Another one is eventual processing requirements. So this is the async separation of concerns, and you have to understand like whether that is okay or not for your use case. And there are a number of knobs you can turn to make Kafka process data faster, but then that also comes with a cost. So you have to trade that off. And then finally, the number of Kafka deployments. So if you're doing any sort of software as a service, you might be making multiple deployments that use Kafka. With anything with data, typically companies want single tenant deployments. You obviously don't want to be mixing different sources of data from different users and customers in a single Kafka topic. So you have to potentially deploy multiple Kafka deployments. And this has an additional cost as well. Maybe if you just have, if you're building an in-house feature store and you just have 1 mega Kafka cluster and you just only need to focus on provisioning that cluster, maybe it's okay. But for any sort of replicated use case, it might not be okay. And so my final point, the title of this slide, the presentation was Going Full Circle with Kafka. And the spoiler that is the full circle is that we eventually returned to a custom sync that's a far more elegant version of the UDF approach. We used a lot of the lessons learned from Kafka as well as the initial UDF. And we built a custom sync that is a lot more reliable, and it has significantly lower operational cost. And so with that, we completed the full circle to and from Kafka. And I know we're right up against the hour, but if there are any questions, feel free to email me. The Tecton Feast has a Slack community. I have 2 colons in that bullet, but yeah, slack.feast.dev. So feel free to join the Slack community. There's a lot of people there. And then we're also hiring. Again, I'll mention we're hiring. We're hiring full stack software engineers, data infrastructure engineers, front end engineers, senior DevOps engineers. So pretty much the entire product and platform experience, we are hiring for it. So if any of that sounds interesting to you, hit me up. And thanks for having me on the meetup.
Absolutely fantastic. Finished literally pretty much right on time. We still got 2 minutes. I mentioned this before we got started. And once again, thanks for all the questions. Ravi, we will be continuing the conversation in Slack. Got a few questions. Also took some screenshots so we can have some context there too. But as I asked you before we got started, you're obviously a very active engineer. You're constantly out there looking at new stuff, trying new stuff. This was a great, and just a shout out to Tecton and the way in which this was done. We've had a lot of presentations. As I said, this is meetup number 50. Take heed here for all the folks in the audience. These are the kind of presentations we're looking for, not just a vendor pitch. Great technical walkthrough showing us how the approach was done. And then at the end, as you said, that based on the use case, that this didn't necessarily match up, but it doesn't mean it's not an adequate technology for other use cases. Like I said, though, you're very active going out there looking at different things. What are your go-to resources? What would you recommend?
I think you really actually learn a lot. Ironically, you learn a lot from talks like this from other companies. So, we recently had the Tecton hosted the Apply conference, which was pretty much like an operational ML, ML ops conference. And there were a number of talks that we've been slowly going through after the conference, and learning kind of these, pitfalls and gotchas and, places where people trip themselves up at other companies really paints a very clear picture of a lot of technologies, like whether it's a good idea or a bad idea. I mean, there's your obvious resources, like, the O'Reilly books are fantastic. Like, you just sit down and read it over a few hours. It's great. but I think like learning the adoption stories from different companies, and I think and that's what makes like, data on Kubernetes so cool. Like all these different MLOps communities or Tecton Feast community. Like,
shout out to the MLOps community as well.
Oh yeah. So, that's what makes them so cool, because there are a lot of companies dealing with these issues. And so it's not like, you're not in a silo where you have to learn the ins and outs of Kafka. There are a million blog posts and talks out there about like all the different ways that people, twisted their ankle running Kafka. And I found that really is a really valuable resource. And, I think it's like, if you're exploring a new technology, it's really helpful to try and source like, a couple talks like this that you can learn from, and hopefully you get something useful out of it.
I think it's a great point. And as you said as well, giving talks too, I think is, really puts you in that sort of reflective mode where you can trace back all the different things, the decisions that were taken, and seeing what was, the definition of success and how things end up working out. Last thing, if you had to define data on Kubernetes is for you, well, how would you define that? Just a quick sentence.
I would say it's not a solved problem.
I think that's why we're here. I think that precisely that's the reason we have this community, is trying to figure out what does it really mean? What's this landscape going to look like? So
yeah, I mean, if I had said it was a solved problem, you can just pack up and go home. We're done.
Exactly. That being said, we got one more thing. Can you stop sharing your screen so I can share mine?
Yeah.
We have a little bit of a tradition. And we will have something special coming out later too as well, later on today. But every time we've done our meetups, we always finish with some graphics. We have our graphic recorder, Angel, who's been drawing what you've been talking about live. So let me know if you can see that. Wow. So we get a nice visual summary of all the stuff that was kind of covered there. It's just a nice way to visually represent that. Once again, generating resources to make these concepts more tangible. So we'll pass that on in Slack. Like I said, we'll have the questions in Slack as well too. We said it before, we said it again. Tecton is hiring. You could work with Ravi. Obviously, a very competent engineer, knows what he's talking about. Great presentation. Great way to do our 50th meetup. Ravi, thank you very much. We'll continue the conversation in Slack.
Great. Thanks, Bart. Thanks, everyone.
Thanks a lot, everybody. Take care.
Bye.
Bye-bye.